So the next problem is 2.1 from homework. A metal sheet with two thin slits is placed 1.5 meters in front of a projector screen. Light with a wavelength of 589 nanometers shines upon the slits. This is the wavelength of light produced by a common type of light source made with sodium, i.e. old lights, old street lights. I love the ambiance of this color of light. It's eerie and nearly monochromatic. On the screen, a pattern of alternating bright and dark spots appears. 13 bright spots are clearly visible, roughly equally spaced around a central bright spot. The distance across all 13 bright spots is 52 millimeters. What is the distance between the two thin slits? You'll notice that I've drawn this screen a little bit curved because that's what catches our angular displacements nice and evenly. If we're referring to a point on the screen, we are referring to a specific angle. Typically, it's up to you to draw what these bright fringes look like, which of course, I guess I'm doing all of this for you, but it's part of the problem. It's not just given in the problem, is what I'm saying. We have to think, it's two slits, so in the very center, when we're coming together, are they in phase or out of phase? Did we move some path length difference that will cause constructive or destructive interference? And you might eventually just be able to memorize the answer, but it's important to be able to go back and say, they are going to the center fringe, and at this central fringe, they've traveled the exact same distance, meaning that they are in phase and they superimpose to make a nice bright fringe. So that's well and good. Then we say, how do we draw the rest of this? We have 13 bright spots that are roughly equally spaced around this central bright spot. 13 means 1 goes to the center. This is 1. 2 through 6. It's actually 2 through 7. Yeah, okay, I can count. So we've drawn our picture. The big first hurdle in doing any of these problems. And they are spaced about the central maximum with approximate spacing of 52 millimeters. So the question is then, what is the distance between the two thin slits? So the first thing we need to pin down is what is the interference condition that we're interested in. And when I say condition, I mean our constraint on our path length based on constructive or destructive interference. So at our first slit, we already said that our path length difference, or our first fringe, our path length difference is 0. They have the exact same difference. Our second bright fringe corresponds to the first place where they've gone out of sync and then resynchronized after a full lambda. Of course, I forgot to write that lambda in beautiful orange, which is 589 nanometers. Come back to that later. Alternatively, you could think of this as the general form. You could think I need a delta L that is n lambda, and my two n's here are n equals 0 and n equals 1. We then know, based on the geometry of the double slit experiment in general, that our delta L is going to be equal to our d sine theta. This means that we have a relationship between the size of our slits and our theta, which is our geometry piece. This is how up or down from the slits we've let our beams travel. So we then say, okay, geometry we don't really have a handle on yet. That's going to be our part two, our hidden part two. But we can at the very least write that for these two different thetas, for theta equals 0, the central fringe, we know that our delta L is equal to 0. So we write 0 is equal to d times sine of 0. Theta equals 0. Wow, that was informative. Sine of 0 we see is 0. That checks out. Okay, great. But then we have our second fringe, our first fringe from the center, and we ask, well, in this case, I know it's, what, lambda and d times sine of theta. I don't know what that is. Okay, well, if that's true, then we have to pull out some elbow grease and figure out precisely what that theta is. So the part 2 here is geometry. This means we have to draw some, you guessed it, triangles. So I'm going to draw a little one here, and we know that this angle is theta. And because we have the qualification from the problem that this is about 52 millimeters and they're about evenly spaced, that means that this little segment on the curvy part is about equal to the length of the not curvy part. So we're just going to use that as if it were a triangle. And it's going to make our result slightly imprecise, but that's an approximation that's allowed here. The geometry here says that we have this triangle where we know that our bottom part is about equal to 0.15 meters, and our other leg is equal to 0.52 millimeters, which I am going to convert into meters. So we have that it's a right triangle, we have two of the sides. This is a lovely, lovely red flag that we should perform some sort of trig. We need to relate all these three variables with a trig ratio. And since it is the opposite and adjacent sides that we know, we can use the TOA, the tangent of theta, is equal to opposite over adjacent. And again, I will use my Emerald Lagasse skills to inverse tangent this, giving us 0.03465 for good measure radians. Radical, dude. And we can take this now and say, oh, well, back to here, we now know what lambda is, what d is not, and what theta is, so we can solve for d and say, I'm gonna figure out your number. I got your number, dude. We discover that our slit separation is equal to 17,000 nanometers, converting to something a little more reasonable. This is either 17 micrometers, which, like, what the heck are those? It's just 3 powers of 10, but 0.017 millimeters, which are a little more familiar. This is, like, pretty tiny, pretty hair width. Small slit separation generally corresponds with a larger pattern separation. So, meaning that we can see really tiny things with relative ease. That's the benefit of this as an imaging technique, as we talked about with DNA. So to recap, we drew a lovely image, characterized the problem, We figured out that for the first bright spot, we have an interference condition of n equals 1, aka our path length difference is equal to lambda. We go ahead and compare that to what we know about general double slits. This is true generally. And we then compared to the geometry of the problem, figuring out that our theta is a particular value, plug that in, and then figured out our slit separation. Ta-da!